Okay, guys, so continuing our discussion on vectors, we're going to kind of extend that discussion a little bit today. Before we get into it, just a different form that you might see on these vectors. So we're used to dealing with this component form or having vectors written as position vectors. But we can write an equivalent form of a vector. It kind of looks like a combination in statistics where you have the two parentheses and then the first component or the x component of this vector is going to be in the top. So this is the x component. And in the bottom is going to be the y component. And again, these represent the exact same things. A here would be the change in the x direction. B here would be the change in the y direction. And so just a quick example down here, the position vector 7, 2 can be written in this equivalent form. All right, so the focus of this video is the dot product. And there are a couple different uses of the dot product. Before we look at those applications or uses, we want to make sure that we understand how to find it. It's a pretty easy calculation, but I don't just want to show you how that thing is calculated. I want to hopefully kind of give you an idea of what this thing is. So the dot product is what we're focused on, and we're going to do a little demo real quick here first. So in this little app here that I've embedded, you can see you've got this these vectors written in that new form that we just talked about. So this is the vector 3, 5, this is the vector 3, 0, and in the middle here is the dot product. And so I want you to notice we're going to start off with the vectors 3, 5, and 3, 0. And here are those vectors. And notice that the dot product is 9. So what we're going to do is we're just going to slide these vectors, change these vectors around a little bit. First thing I'm going to do is I'm going to take vector B and I'm going to slide it out to about 4, 0. So I've taken vector V and just slid that vector out, essentially just made it longer or increased the magnitude of it. Let me write these results real quick over here. So the first one was 3 times 3, and that gave us a dot product of 9. And the second one, we took this vector, slid it out to 4, increased the magnitude on that thing, but didn't change the y direction. And we've got a dot product of 12. So now I've got 3 times 4 equals 12. Next thing I want to do is I want to change the y direction. Let's see what happens to the dot product of that thing. So we take this vector, we slide it up to 4, 1. So we have again increased the magnitude, but not in the x direction. We didn't change the x direction. We changed the change in the y direction. So look at what happened to the dot product. We've now got 17 for our dot product. And so let me write these results. The dot product is 17. And so if you notice what's happening, the change in this dot product from the previous one where we just had our x component, our x components were giving us the product of our x components, were giving us the dot product. Now that's not necessarily the case because I've got my 3 times 4, the product of my x components, but we've increased by 5, and so what I need is to figure out where that increase came from, and where it comes from is the y. And so I've increased this, the change in the y to 1 here, and you can see that that increase comes from this product right here. So we've got the product of 5 times 1, and we just added that product. All right, we'll do it one more time. So let's change one more of these components, and I think hopefully you kind of see the pattern. Let's go to, I don't know, something nice round numbers here. Let's go to 5, 6. We can see the dot product is now 26, and that is 5 times 4. And I'm adding the product of my y components. And that gives me the dot product. And so generally, if you had to describe what was going on here, basically the dot product is the sum of the products of the components of each component. What I mean by that is I'm taking the products. This is the x component of the first vector, x component of the second vector. I'm multiplying those together. This is the y component of the first vector, the y component of the second vector, and I'm adding those. So it is the sum of the products of each component for these vectors. And it turns out that that's exactly how you calculate the dot product, is the sum of the products of each component. So the general form of this thing, if I've got vector A with components A1 and A2, vector B with components B1 and B2, then the dot product is the sum of those products. So it's A1 times B1 plus A2 times B2. That gives me the dot product. So the major thing that I really want you to take away from this is that, number one, how to calculate the dot product, but number two, that the dot product is a scalar. It's a number. It's not the result of the dot product is not a vector. And again, we can go back to those calculations we just did. Scalars, all scalars. And so when we calculate the dot product, we're just calculating a scalar for these vectors, or with respect to these vectors. So let's go check this out, do a couple dot products just as examples. First thing, we've got these three vectors, v, w, and x, with their individual components. We want to calculate v dot w. So v dot w is going to be, v looks like 8, 4. Dot w is 2, 1. And so we take our x components, multiply them together. Eight times 2 plus 4 times 1. So we get that v dot w is equal to 16 and 4, which is 20. Same thing over here, w dot x. So w is 2, 1. Dot x is 1, negative 2. That's an x. Go through and calculate, and we get 2 times 1 plus 1 times negative 2. And this dot product happens to be 2 minus 2 is 0. And we'll come back to these in a second. So a couple of the things that we want to look at with respect to dot products. Number one, parallel vectors. Parallel vectors are essentially just vectors where one is a multiple of another. So the general form looks like this. If I take v and I multiply that thing by some scalar, and in this case the scalar is m, then v and w are considered parallel vectors. In other words, if w equals some scalar times v, then they are parallel vectors. So if we go back to this example real quick, example 1, v dot w, you can see, hopefully this is a pretty easy one, you can see that w is actually a scalar of v, and vice versa. V is a scalar multiple of w. And so since w is some scalar multiple of v, v and w are parallel. And just to confirm that, we go up to here, v and w. So w is 2, 1. And what do we multiply 2, 1 by to get, what do we multiply v by to get 2, 1? Well, we multiplied it by 1/4. So my scalar in this particular case is 1/4. And when I take 1/4 and multiply it by vector v, I get w. So they are in fact parallel. So if we look over at example 2, we can see these two vectors. There's no scalar multiple that there's no number that I can multiply this particular vector w by in order to get x. And so therefore these are not parallel vectors. There is no scalar that exists where I can create one vector out of another essentially. And so that creates a different scenario, and that's what we call orthogonal vectors. And orthogonal vectors, orthogonal is just another name for perpendicular. And so it turns out that perpendicular vectors, if we look at the dot product of perpendicular vectors, it's always going to be 0. All right, so two vectors are perpendicular or orthogonal. I spelled that wrong. There we go. If their dot product is 0. And so again, we go back to our example that we did. Example 2 here, W and X. We look at their dot product, and their dot product is 0. So we say since W dot X equals 0, W and X are orthogonal. Let's see if I can spell it right this time. So down here we have a couple of examples. We want to find some vectors that are parallel, and literally all we have to do is find any scalar, multiply it by that particular vector, by vector A, by each component, and we'll come up with a parallel vector. Same thing here. Find a scalar, multiply it by each component, and you'll find a parallel vector. So I'll leave that to you. So what we want to look at next then is we now know how to calculate the dot product if we have the components. So we want to look at some other uses of the dot product. So the first thing that we want to check out here is essentially, notice here that we've got this vector A, and it's defined as having a magnitude of A with direction alpha. B has a magnitude of B with direction beta. And again, notice if we want to calculate the dot product, we don't have the components, and so we can't necessarily use that formula that we just came up with, the sum of the product. So we want to look at maybe a different way that we can do this. First thing, we want to write these as position vectors. And so if we write these as position vectors, vector A can be written as, if we want to find the change in the x direction, we're going to write this essentially as a force vector. And so I want the magnitude of A. So we define that as A up here. And we can write if we're going to write this as a force vector, we're going to have A times the cosine of whatever the angle of A is, or the direction of A is, and that happens to be alpha. I want the y component. I'm going to write the force vector. This is the magnitude of A times the sine of whatever the direction of A is. So next I want to write B as a position vector, or in component form, however you want to say that. This is going to be the magnitude of B times the cosine of the direction of B, which happens to be beta. And the y component is going to be the magnitude of B times the sine of beta. So we have these two written as position vectors, or in other words, force vectors. And so now we want to go down and find that dot product based on that. So we know that A dot B is just the sum of the products of the x components and the y components. So let's go ahead and write that out. So we have A times the cosine of the direction of A. We're going to multiply that by B times the cosine of beta, which is the x component of vector B. And we're going to add that to A times the sine of alpha, multiplied by the y component of B, which is B times the sine of beta. Next step here is we've got an A and a B common between both of these terms. And remember, that's really just the magnitude of A and the magnitude of B. So we can pull that out in front, and we're going to multiply that by whatever's left over. So what's left over is the cosine of alpha times the cosine of beta plus the sine of alpha times the sine of beta. So we're going to pause right here real quick on this little manipulation. I want to focus on this expression right now. We know what the magnitudes of each vector are, and the definition of those and how to find those, but I want to look at this expression right here. And this is actually a pre-calculus thing. We're not going to worry about proving it. This is called an angle difference identity. And so here's the technical version up here. The cosine of the difference of the two angles of our vectors. So we have vector A has an angle, or a direction, I should say, of alpha, and vector B has a direction of beta. And so why this is important is because we want to look at the angle that is created between these two vectors. So if I take the direction of A, which has this angle right here, and the direction of B, and I subtract those two, what I'm left with is the angle in between these two things. And so the trig identity that we're going to make use of here is that this expression, and hopefully that looks familiar, that's the one that we're focused on, the sum of the products of the cosine of each of these angles and the sine of the cosine, or I'm sorry, the sine of each of these angles is actually equal to the cosine of the angle between the two vectors. And so generally what that means is we can just take this expression and we can substitute this in. And remember, alpha minus beta is the angle between our vectors. Vector A and vector B. So for right now, for our purposes, we're not going to worry about proving that this works. If you want to, you can try these couple examples, plug it into your calculator. So we would just plug these values into our calculator and make sure that those are equivalent expressions. It does work. Go ahead and confirm that on your own. But again, what we want, or what we're interested in is that we can take this expression and sub in this equivalent expression into the manipulation that we're doing right now. And so we go down to our manipulation, cosine of alpha times cosine of beta plus sine of alpha times sine of beta. We can substitute in the cosine of the difference between our two angles. And that's multiplied by the magnitudes. So we have the magnitude of A times the magnitude of B times the cosine of alpha minus beta. And this is all equal to the dot product of our two vectors. So we move some things around. We want to isolate this thing because we're interested in this thing, and I'll tell you why here in a second. But in order to isolate that, we just divide by the magnitudes of each of those. And what we're left with is the dot product of A and B divided by the magnitude of A times the magnitude of B. And that leaves us with the cosine of alpha minus beta. And again, why is this important? Because alpha minus beta, that gives us the angle between the two vectors, between vector A and vector B. So taking this one step further, in order to calculate the angles between these two things, I need to undo this cosine function. And in order to undo that, I just need to take the inverse cosine. So if I take the inverse cosine of the dot product between the two vectors, divided by the magnitudes of these two vectors, that allows me to solve for the angle between the two vectors. So one of the reasons this is nice is because we don't need the components of each of those vectors. And generally, we won't have the components of each of those vectors because vectors are defined by their magnitude and their direction. And so we can go through and solve based on knowing the magnitude of each of those vectors and the dot product in order to find the angle that's created by two vectors. So let's go ahead and check out an example of this. So here's your formula up here. The cosine of theta is equal to the dot product of the two vectors divided by the product of the magnitude. So we've got these two vectors A and B. We want to find the angle between these two vectors. So the first thing that I need is the dot product. So A dot B is going to be equal to 4 times 5 plus 3 times 1, which is equal to 23. So there's the dot product. I also need the magnitudes of these two vectors. So the magnitude of A is going to be equal to the square root of 4 squared plus 3 squared, which is 16 and 9, which is 25. So that's equal to 5. And then the magnitude of vector B is equal to the square root of 5 squared plus 1 squared, which is root 26. And so I can now go up and plug this stuff into my formula up here. So I know the cosine of the angle that we're interested in between the two vectors is equal to the dot product, which we said is 23, over magnitude of the first vector times the magnitude of the second vector. So the cosine of the angle between the two vectors, a little bit of calculator work, is equal to 0.902134. And take the inverse cosine of both of those, both sides, and you end up with the angle between these two vectors is going to be 25.56 degrees.